Hey, welcome everybody. Mr. Bruss here with another biology recap. Today I'm filming on location in my kitchen, and we are recapping today, Thursday, September 17th. Today was another great day in class. We started off with a little fun from our graph of the day, which was a clip from Brain Games where we talked about mnemonic devices. We rolled that into a little bit of research on how people learn. And we looked at this graph that details that testing yourself rather than simply studying, rereading, but actually like creating tests for yourself is a great way to improve your memory and retention of material that you've learned. And we thought that was a really nice little segue into introducing a resource that we have available for all of the bio students in Canvas. And I'm just going to share my screen over here so that I can show you or remind you, if you were in class, where you'll find this resource and how to navigate it a little bit. So here we are in Zoom. I'm going to pop over to Canvas once it loads up there. And I'm going to click on my class. And I changed the front page a little bit on my class, but for the other classes, that won't matter too much. So down here in modules, and I think for every class, it looks basically the same. If you scroll down from your ecology module and you click on ecology test review materials right there. And there are two ways that you can look at this review test and review concepts. One, they're both the same. One you could find in Google Docs, and the other is a PDF that you could open up in Notability. So I'm going to click it up here in the PDF, and I'm not going to send it to Notability because we have videos and you've seen that a few times. But what we have here is the 17 concepts that we're testing on our final assessment for the ecology unit. And the way this was created is we just went through the test question by question, and we certainly not going to tell you what the question is because then you won't really study and you won't really learn these concepts. Something about studying and not necessarily knowing what the question is going to be kind of drives you to study, and that's where the real learning comes in, and that's actually what we care about the most. But what we did is I looked at every question and then said, okay, what is the general concept that this question is going to ask? And I put those concepts here, 1 through 17. We talked about in class that we've basically covered up to this point 2 through number 13. Actually, we've covered up to number 14 in class today. Numbers 10 and 11, we need to actually 10, 11, and 12, you're going to want to learn in a little bit more detail. And we have an asynchronous session on one of the Mondays where you're going to learn a little bit more about that. But other than that, we've covered almost every one of these. And the way this works is here's the concepts here. And this is you can see up in the top left here. Oh, and it doesn't do it when I go like that. If I move this, oh yeah, there it is. You could see it was 1 of 23. So it's a 23-page document. And these hyperlinks link you to just lower in the document. And they link you to some practice questions. So if I wanted to practice creating a food chain from a food web, I'd click on this. And what you're looking at here is 5 practice questions that are based off of the question that's actually asked in the test on this concept. And you can test yourself here, and we'll be posting a key to this soon. And when you have that key, don't just look at the answer right away, but really test yourself and see, do I know, can I figure this out on my own? Then you can go to the answer and see if you got it right, or maybe you can work backwards from the answer and see how see what you missed. All right, so I just wanted to quickly say, we went over this in class, that this document is available for you and you can start working on it immediately. And a great place to, once you've been working on this, to think about it more deeply or to ask questions would be those office hours, 8 to 10 a.m. and 3 to 4 p.m. We're ready I know Mr. Austin, Ms. Klepper, and Mr. Monzon have been doing great work, and they're always available from 8 to 10 and 3 to 4. Okay, so after that, we moved on to the homework, which was graded Ecology Graded Practice 4, and we just went into reviewing this homework. So we started off with students watch this YouTube video here, and these questions are based off of the content that the speaker in the video gave. And so the first question we went is, what is a predator? Well, a predator in a predator-prey relationship is the one who eats the other one, right? And I think we kind of have a sense of that. And we showed a little like Wile E. Coyote versus Roadrunner video in some classes. And Wile E. Coyote is trying to be the predator there, but always gets fooled by the Roadrunner or mishaps. So then we talked about, what is the prey? The prey is the one who gets eaten. And we talked like, yeah, we kind of know these words. It's maybe not anything new to anyone. But what might be new is interpreting these in a graphic form, using a graph to see how they're related. We also mentioned, just like the speaker in the YouTube video mentioned, that when we're talking about predator-prey relationships in an ecosystem, we're not talking about single individual animals, Wile E. Coyote and the Roadrunner. We're talking about whole populations. And in this case here, we're talking about whole populations of foxes and whole populations of rabbits, all of the animals that live in that space. So then we went over and looked at this graph and we said, okay, we need to label the X and Y axes. And we were reminded that in a math class, what you would write here is maybe you would just literally write X axis. And here on the vertical axis, you would literally write Y axis. But in a biology graph or a scientific graph, you want to provide a little bit more detailed information. Yes, this is the X-axis. Yes, this is the Y-axis. But what more can we learn from that? And what we saw was that on the X-axis, that is time in years. And we talked about if time is in a graph, it's always on the X-axis, right? Because it's the independent variable. And in this, on the Y-axis, what we're talking about is population number. We talked about what is this term for the largest population of prey. So we see up at these little peaks, that's where the prey population is the largest. And we call that spot, we call that the carrying capacity. It reflects the carrying capacity of that ecosystem. And we talked about why can't the rabbit population just keep going up and up and up and without a limit? And we posed that question to students, and all the students, you all came up with all of the reasons why you can't. There's not enough food. The rabbits need to eat something. And if the population keeps growing and growing, they chew down all of the grass, the plants that are there to eat. And it was very similar to the situation when wolves were removed from Yellowstone National Park. The elk population grew and ate down all of the food. And eventually that population probably dipped and went through these cycles. The other one that students mentioned is, as there's more and more rabbits there, there's more and more food for the predators, for the fox. So the fox will eat more and more rabbits and kind of keep a limit to how many there can be. Students also came up with a great one, that disease, when you have a lot of animals together in a smaller space, the diseases are passed on much more readily, and animals can die from the disease. In addition, there's a limit to the amount of space. There's the habitat, there's certain places where rabbits want to live and nest up, and there's a limit to that. You can only fit so many in a space. So then we went on and started talking about if this prey population increases, what would you expect to happen to the predator population? Well, since the predator's population, the predator's food is the prey, we would expect that the predator population will increase along with the prey population. We did notice a couple things though, that if that were to happen, that when the prey population rises, it takes a little bit of time for the predator population to respond, right? And we call that it lags behind. The predator population sort of lags behind whatever's happening in the prey population. And that kind of makes sense, right? So the predator population can't just explode without a food source. And the food source is the prey. So the prey's population needs to increase first to provide that food for the predator population to then increase. And as the prey population increases and increases, we know that they're eating up the food in that area. The predator population is now increasing, which is feeding on these prey, and maybe predation is happening, starvation is happening, and this prey population is falling. And once it reaches some minimal level, now there's not enough food for the predators. So the predators population starts going down. The grass that the rabbits were eating is now growing back because there's not as many rabbits to chew it down. And now the prey population kind of comes back up. And again, the predator population, which was now low because the prey population was low, kind of follows it up. So the prey and the predator population go through these cycles. And when they go through the cycles, the predator population lags behind the prey population. So that was a couple of these key observations that we made. Both populations go through this cycle, and the predator population lags behind. One other thing that's interesting that you'll notice in this graph is that the prey population is always much larger than the predator population. And this is sort of a stylized graph, but in pure numbers, the prey population has to be larger than the predator population in a stable ecosystem. And the reason for that we talked about is very much related to these trophic pyramids that we learned about yesterday. And in a trophic pyramid, what we can see is the producers, the grass, are on the bottom of this pyramid. Primary consumers, rabbit, are at the next level, and fox, the secondary consumer, is up here at the top level in this pyramid. And the reason it is shaped like a pyramid is to show that there's way more biomass, way more mass of grass than there are rabbits. And there's way more rabbits than there are foxes. And in fact, there's at least 10 times more. Each level decreases in mass by a factor of 10. So there's practically at least 10 times as much grass as there is rabbits, and at least 10 times as many rabbits as there are foxes. And that's how the energy of the system flows. And so that's why the prey population is always larger than the predator population, and it's related to those trophic pyramids. We did talk a little bit, and we went into this graph and we showed, well, what if let's use this one. What if you drew the grass here, right? Grass is an organism. You could put it on as a population here, and it changes over time. So we kind of graphed out that if prey population was at its highest, grass would be at its lowest. And when prey population is at its lowest, grass would be at its highest, and so forth like this. And so you could draw a similar cycle for grass, but it would be way more than the prey population, just because there's way more mass of those producers. All right, so from there, we moved on to what we were working on today, which was to dive in a little deeper into this predator-prey graph. And we looked at this graph right here, and we noticed a couple things, and I'm going to go through it quickly. We spent a lot of time talking about this graph in class, and I'll try to go a little quickly here. On the x-axis is time measured in years. Then we see that there are two lines that kind of go through this cycle. And if we look at this key here, we see that the lines that have the open circles, this one right here, represents the fox population going up and down. And the line with the closed circles, this one kind of here that I'm tracing along represents the rabbits. And we said, okay, this seems good. But what about what Mr. Bruss was just talking about? Shouldn't the rabbit population be much higher than the fox population? Yet when I look at this graph, it seems like these lines are very close to each other. And that is a little trick of this graph here. And what you can see in this graph is they have two different y-axes. On the left side, the y-axis represents the number of foxes. And so if I look at the year 1985 and I scroll up to the number of foxes, I can see right here that there are 5 foxes in 1985, okay? In 1988, if I scroll up, there are 15 foxes in 1988, okay? So what about the rabbits? Well, we use the right axis over here to indicate the number of rabbits. So by the same token, in 1985, when there were 5 foxes, if I keep going here, I need to now go all the way across to this axis, and I can see there are approximately between 200 and 300, maybe 250 rabbits, because this right axis, the right y-axis, indicates the number of rabbits, and it goes from 0 to 100 to 200 to 300 to 400, as opposed to the fox, which goes to 0, 5, 10, 15. And then we talked about there's a reason for this, right? So if we wanted to have one graph with one set of numbers, right, 0, 100, 200, 300, we could see that the rabbit population would be really well reflected. We would see these dips, and looking at the graph, you can interpret trends. But now imagine this. The highest population of foxes is 20, and the lowest is 0. And each one of these lines here, that line to that line, to that line, to that line, to that line, represents 20 foxes. So if I were going to draw, let me see if I could even do this. If I were going to draw the fox population in here, I'm going to try to be, I would have to draw it all within here, right? Because it's from 0 to 20, and I just kind of highlighted, and you put the graph back, you can hardly even see, you can't really get a good sense of the trend of the foxes because the scale is different. So scientists know this, and they want to draw a graph that people can see, that can interpret easily. And what you want to be able to do is interpret these trends of the fox. So that's why you have to have 2 different numbered scales here. Okay? And so what we then had students do is, on your own, students were going to answer these questions. So which animal is a predator in here? Well, we know that the predator in here is the fox, right? The fox. And which animal is preyed upon? Well, we know the prey from this is the rabbit. All right. How many rabbits were there in 1989? So we know that the rabbits are the closed circles there. So I go over to the year 1989 and I scroll up, and it looks like there is 5, 6, 7, 8, 9 rabbit. No, sorry. Don't caught me there. I was looking at the wrong scale. I go this way. About 180. Oh, it's 20 times more, right? That makes sense. The scale is 20. 180 rabbits in 1989. So 180. All right. How many foxes were there in 1993? Well, let's see here. Now I'm going to use the left axis. 1993 foxes. I go to here. And 1993 foxes there. Over to here. It looks to me like there are 12 foxes in 1993. 10, 11, 12 foxes in 1993. All right. In which year were there the most foxes? All right. Well, that's a little easier. So foxes are these open circles. So I see the peak up here. And yep, that's 21 foxes. And that peak seemed to happen in 1996. So it's asking me in which year were there the most foxes? So to me, that looks like 1996. All right. And explain why the numbers of foxes fell between 1988 and 1990. Okay. So between 1988 and 1990, these years here, the fox population fell. Well, we know that the fox population lags behind the trends of the rabbits. And so if I back up a couple years, I can see from 87 all the way down to 89, 1 year kind of prior, there is a dip in the rabbit population. So my guess is that the rabbit population fell. Rabbit pop fell. All right. Okay. During 1996, the rabbit population was almost totally wiped out. Oh, look at that. So in 1996, the rabbit population was almost totally wiped out. Give one possible reason for this. Well, maybe there was a huge drought in the grass that they were feeding on. Their food supply, for whatever reason, their food supply was gone. Food supply very low. Maybe there was disease. Maybe, right? Could have some unknown disease. Now, let's look back here. In reality, if the rabbit population then spikes up again, usually diseases for animals like this, I think would probably have longer trends, right? We know about this disease that's happening in bats, and that seems to be like a many year trend that's happening. So I would say maybe it's not disease. I bet you there was, based on that trend, I would say it's probably something happened to their food supply, probably a drought. So in 1997, there were no foxes. Give one reason for this. Well, the rabbit population fell to about almost nothing. And these foxes that were sitting here, right, in 1996 without any rabbits. And, you know, they probably lived for a while, but then probably died of starvation, would be my guess. So I bet you it was starvation because there was no rabbits, their food supply. So I'm going to put starvation there. Okay. And that's what we did today. We didn't complete that in class, but we were hoping you all, the students, could work on this on your own and then use this to check your answers. So I'm gonna stop sharing here, come back here, and that is our recap video for Thursday, September 17th. And really looking forward to seeing you all tomorrow on Friday, last day of the week. Yeah, and I will see you all tomorrow. All right, bye-bye.